All right, folks. So in today's video, we're going to take a look at these ununs. And what these are, some people will call them a matchbox. Some people will call them a transformer. Some people call them an impedance matching network. They get called a lot of different things. But in amateur radio, what we do is we use these to match our coaxial cable from our amateur radio to an antenna system. And we hook our antenna systems up to these connectors here. Your aerial or your element goes here, and then your ground or counterpoise goes here. These were made by a buddy of mine. I call him Thump. I think everybody calls him Thump. And they're two different versions. He made a 49-to-1 UnUn's, so this would match for an end-fed half-wave dipole. And then this is a 9-to-1, and this would be for a random wire antenna. Both of these are end-fed wire antennas. A lot of people use them because they're very easy to build, deploy, and use. Very handy, and they perform very well. He built these out of a 3D printed case that he designed and made. This is an ABA plastic. And what's nice about these plastic containers is that they are heat resistant and they are UV resistant, so you can leave them outside for extended periods of time. Now, my buddy Thump is really into shortwave listening, or some people call that SWLing. And he uses SDRs for that and a couple of different radios, and that's something that he's very much into, and he wanted to make some prototype antennas, and he sent these two to me to test out and make a video on. So here they are. You can also use these for amateur radio, and you can use these for transmitting. However, given their smaller size, I would use these on QRP operations. An amateur radio QRP means that we're operating at about 5 to 10 watts of power. I think both of these would work on 10 watts of power. No problem for single sideband. Single sideband, the modulation, the way that works is you're never really transmitting at your full power. Just based off of the modulation level, your power will fluctuate. If you transmit on something like CW or FTA to digital mode, you have a higher duty cycle when you're pushing full power for longer periods of times. And ununs, transformers like this, can get hot. And when they get hot, they don't work as well. The magnetic core inside, we're going to open these up and take a look at the inside and the construction, gets a little bit hot. And when they get to a certain temperature, they lose their magnetic ability to transform impedance. And I'm just keeping that as a very simple explanation for right now. Anyhow, it was really cool of him to build these and send them to me, and let's get these things opened up, and then we're going to connect them to a nano VNA, and we're going to test their ability to transform impedance at various frequencies. So let's get started. Okay, let's take a few minutes to look at the insides, or the innards, as I like to say, of these two devices. So first we're going to take a look at the 49-to-1 UnUn, and when we look at this, the first thing you notice is that we have two connectors up top. And these are they're called banana connectors. Some people call them banana jacks. Some people will call them 5-way connectors because there's a couple of different ways that you can connect these to stuff. But the red is your antenna element, and then the black would be for your counterpoise. And we have a toroid in here, and this is what's called an FT82-43. So the 82 means it's 0.82 of an inch across in diameter. The 43 denotes the mix or the composition of the toroid. And if you take a look here, we have twisted pairs. This is considered your primary. We have 2 primary, and then we have 14 turns total. So when you take the 14 turns, which is called your secondary, and divide it by the primary, you get 7. 7 squared is 49, and that's your impedance ratio. And you can see here we have a capacitor. This is a 100 picofarad capacitor that is shorting the positive to negative, or you would say the center conductor to the shield, or to your ground. Also, the ground for your counterpoise comes down and is connected to this ground as well. Pretty good construction, and I'm excited to test this one. Now here we have a 9-to-1. And what I've done is I've added an artificial load to simulate our antenna, and this is 451 ohms. That's as close as I could get. And so when we apply the 9-to-1 impedance ratio, what we're going to get is a 50 ohm resistance or impedance here at our antenna feed point. That's what we should get. Now, if you take a look, we have the same banana jacks or banana connectors, and we have the same toroid, but it's wrapped differently. We have 9 turns of 3 pairs, and this is called a trifilar wound toroid. Once you wind the wires on here, there's a procedure that you need to do to connect them up correctly. Now, I've got a ton of videos showing how to make these ununs if you're really that interested in them. And I also have videos showing the different number of windings. I believe we did 5, 7, and 9 and compared the efficiency scores. And I prefer to do these with 9 windings on them. I find that works best. Also, we have a piece of double-sided sticky tape down here to hold the toroid in place. Here, there's enough solder connections to hold it in place, not to worry. I think I showed this already. It's a 9-to-1. So what I want to do is I'm going to connect this up to our nano VNA. And we're going to use our channel 0 and do an S11 measurement. And so that allows us to get the reflection coefficient. So we're going to shoot a signal out of the nano VNA along this coaxial cable and into the antenna feed points. And then we're going to measure what bounces back. SWR causes a return wave. And the ratio of our forward power to reverse power will give us our SWR reading. And as I mentioned, what we're going to do is we're just testing the ability of these to transform impedance of the expected load, our antenna, and convert that into a 50 ohm reading. The other thing I was going to show is for the 49-to-1, I made another load here, and it's just 2 resistors. And this gives us about 2,525 ohms. That's as close as I could get it. What you expect with an end-fed antenna on a 49-to-1 end-fed half-wave dipole is that you would get 2,450 ohms. So we're about 100 ohms off, but we still should get an impedance match of around 50.5 ohms of impedance. So it's going to be close enough. It's going to tell us if this thing's doing its job or not. Also, I just want to mention that for a random wire antenna, which this one is, the length of the antenna is actually not really random. It has to be a length that is non-resonant on any amateur radio frequency or harmonic thereof. Again, I have some videos explaining a lot about wire antennas. I'll actually link it in the description below, and you can check that out if you wanted to see that, to learn a little bit more about these things and how they're used. Let's get these connected to our nano VNA. We're going to come back with nano VNA saver, and we're going to do a sweep. Okay, so the first thing we did is a sweep of the 49-to-1 UnUns, and you can see the results here. In the upper left-hand corner, what you can see is a sweep control settings, and we are sweeping from 1.5 megahertz to 30 megahertz, and this will cover from the 160 meter to the 10 meter band. And we have this divided into 10 segments. Now, because we're doing a quick and easy test and not an in-depth analysis, what we have our nano VNA set to is 101 data points. With 10 segments, we are going to get 1,010 data points across our sweep. You can increase the number of data points on your nano VNA depending upon the model, and you can increase the number of segments that you have, increasing the number of points on your overall sweep. Now you can see here at the lower bands at 160 meters, you can see that these points are very far apart, and that is because we have a limited number of data points, but this gives us enough data to accurately do an analysis on the results that we want. So when I take a look at this, there are a couple things come to mind. The SWR is very high when we look at 160 meters, and that is because of the mix of the toroid. There are other mixes that you can use that give you better performance on certain frequencies, and this is what I would expect. Now when we come down here at, say, the middle of our 160 meter band, say somewhere right around here, we can look at our marker table and we can see that our SWR is around 5.2 to 1. Now this might work fine for listening, but in terms of transmitting, I would not transmit on that. Potentially you could use a tuner on your radio and get a little bit better results. As mentioned, I would use these for QRP operations, somewhere around 5 to 10 watts if I was going to transmit. When you use a mode such as single sideband, the amount of power that gets put out is largely dependent upon the modulation of the information being applied to your carrier signal. Well, actually, single sideband strips the carrier signal off, but nonetheless, it's based off of the modulation strength. So you don't really get a full power output. If you're doing a higher duty cycle mode like CW, continuous wave or Morse code, or something like FT8, which is a digital mode, or RIDI, which is another popular digital mode, you have a higher duty cycle and full power goes out for the duration of your transmission. This can cause the magnetic core inside of your transformer or UnUns to saturate with heat, and it reaches what's called a Curie temperature, where the core is no longer magnetic and loses its ability to perform the impedance transformation that's so important to us. So I'd be very careful in testing these out on transmit. I would keep an eye on my SWR on my radio, and I would maybe check the temperature of these things and make sure that they're not hitting that saturation point. When we take a look at the 80 meter band right here in the middle of it, or somewhere about that, we have a 1.999 to 1 or 2 to 1 SWR. And you may be able to work this with the tuner, no problem. Same thing with the lower 160 meter band. But I think I prefer to have this somewhere, given that it is supposed to be a resonant antenna, I would prefer this to be around 1.5 or less. If we jump up to the 40 meter band, in the center of that, we are 1.5 to 1, which is pretty good. Pretty happy with that. Around 20 meter band here, we are at 1.9, close to 2 to 1 SWR, which is a little bit concerning, but it's not a showstopper. Above that, I would really think about looking at the design of this UnUn. I would check all my connections inside, and you could potentially adjust the number of secondary windings if you want. But the capacitor that we looked at, I would go back and I would make sure that that capacitor is of the correct value and is working correctly. Typically, we use the capacitor to kind of smooth out the higher bands and get a lower SWR, and that doesn't appear to be the case here. So, for example, if we look at the 10 meter band, we're at about a 3 to 1 SWR, and I think I would go back to the drawing board on that 49 to 1. And you can see that we're better off in the lower bands than we are in the higher bands. It actually looks really good down in the lower portions here, like in the 80 meter band. If I go ahead and I just highlight, I can get my marker number 1. You can see in the marker table, our SWR is 1.024 to 1, which is fantastic. And it increases as we go up, and that is typically expected in some of these things. And you can look at different core compositions to keep your antenna more resonant in the frequencies of interest to you. As I mentioned, my buddy who put these together for me, Thump, he uses these for shortwave listening, mostly in the lower bands, some high band activity, but even all the way up in the 10 meter band. Let me just go ahead and highlight at the top edge of that. Our VSWR or SWR is 1.397 to 1, which is a very good SWR. So these should work relatively well for a receive-only antenna, which is what my friend does. He does that on SDRs mostly, and likes to listen to amateur radio bands and shortwave frequencies, and this should work just fine for that. I would limit any transmitting and QRP type operations on these UnUn's to 10 watts or less. They should work fine for 10 watts in a single sideband. If I was doing digital modes, which has a higher duty cycle, the cores could heat up a little bit, and I would think about maybe potentially limiting my power output to 5 watts, but I would test that out and make sure. But that looks really good. So let's talk about the test that we did on these particular UnUn's. One of the things I want to mention is that the resistors that I used here are just normal resistors. They're not non-inductive resistors. So they can have some reactance that does impact or affect our results. I feel pretty confident in what we saw. And one of the things I'll say is if you want to see a real world results, what you would need to do is you would need to hook these up as an antenna and then do some sweeps there. Maybe we'll do that in the future, maybe not, I don't know. But I think that's really going to wrap up this video. I do want to say thanks for watching. I appreciate it. Thanks to Thump for sending these to me to test out and play around with. If you have any questions, comments, suggestions, or recommendations, go ahead and post them below, and I'll do my best to respond. Thanks for watching, everybody.